Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve this rather long problem, which is divided into 3 steps. In each step we attempt to prove something, and the previous problems will act as hints or lemmas that can help us solve the next problem. First, let's read the problem once to see what this is all about. For problem A, suppose m and n are integers. Prove that if the roots of the quadratic equation x squared plus mx plus n equals 0 are rational numbers, then these roots are integers. In problem B, now consider the polynomial fx where all of its coefficients are integers. For arbitrary integers a and b such that a and b are different, prove that fa minus fb divided by a minus b is an integer. And for problem C, for the polynomial defined in problem B, suppose that for some integers a0 and b0 such that a0 and b0 are different, fa0 times fb0 is divisible by a0 minus b0 squared. Then prove that fa0 divided by a0 minus b0 and fb0 divided by b0 minus a0 are both integers. So we are going to solve this problem step by step, and let's start from the first one. For problem A, let us use the famous proof by contradiction. That is, the roots of the given equation are still rational numbers, because that's the condition given in the problem. But let us deny the conclusion and suppose that they are not integers. Then we can express the roots as x equals p over q, where p and q are co-prime integers and q is not equal to 0, because they are rational numbers. We will draw contradiction from this assumption. Here, q equals either plus 1 or minus 1 is a trivial case, which makes the roots obviously integers. So let's consider the non-trivial case where q is not equal to plus minus 1. That is, x equals p over q is not an integer as we intended. Then, substituting this root into the quadratic equation, we have p squared over q squared plus mp over q plus n equals 0, and we can solve for n, which gives n equals minus p squared plus mpq divided by q squared, which can be written as minus p times p plus mq divided by q squared. Here we will use the given condition that n is an integer. We must also consider that q is not plus minus 1, and p and q are co-prime, hence p cannot be the multiple of q. So this p cannot be the multiple of q, then in order for n to be an integer, this p plus mq must be the multiple of q squared. That is, p plus mq equals kq squared for some integer k. Then we have mq equals kq squared minus p, and since q is non-zero, dividing with q gives m equals kq minus p over q. So p over q equals kq minus m. But by our assumption, the left-hand side is not an integer, but the right-hand side is an integer. This is a contradiction. Therefore, we have the conclusion: if the given equation has rational roots, then those roots are integers. Now the second problem. Here, the general expression for polynomial fx is fx equals coefficient cn times x to the power of n plus coefficient cn minus 1 times x to the power of n minus 1, and so on, all the way to c1x plus c0. And the degree n is a natural number. So using this general expression, let us calculate fa minus fb. Then we have fa minus fb equals Cn times a to the power of n minus b to the power of n plus Cn minus 1 times a to the power of n minus 1 minus b to the power of n minus 1, and so on, all the way to C1 times a minus b. And the constant term C0 just cancel out. So we have this. But we know that for an arbitrary natural number m, we have the following factorization formula of a to the power of m minus b to the power of m, where a minus b is always a factor. That is, a to the power of m minus b to the power of m is divisible by a minus b. Therefore, a to the power of n minus b to the power of n, a to the power of n minus 1 minus b to the power of n minus 1, and a minus b are all divisible by a minus b. Meaning that fa minus fb is divisible by a minus b, making fa minus fb divided by a minus b an integer. And this concludes the second proof. In the final problem, where we have to prove that these two are integers. But before we dive in, let us reflect on what we have proved in previous two problems. In the first problem, we have proved that the rational roots of this integer coefficient quadratic equation must be integers. And in the second problem, we have learned that for an arbitrary polynomial fx, this expression is always an integer. So let us think about it in this way. What if we construct a quadratic equation having these two values as its roots? In order to construct a quadratic equation, we have to use the relation between roots and coefficients. First, we need the sum of two roots, which is fa0 divided by a0 minus b0 plus fb0 divided by b0 minus a0, which gives fa0 minus fb0 divided by a0 minus b0. And hey, this expression looks familiar. We have seen this in problem B. And by the conclusion of that problem, this number must be an integer, so we can let this expression equals capital M, which is an integer. Next, let us calculate the product of two numbers. This gives minus fa0 times fb0 divided by a0 minus b0 squared. Here we use the final given condition that fa0 fb0 is divisible by a0 minus b0 squared, which means that fa0 fb0 equals a0 minus b0 squared times n for some integer n. Using this expression equals minus capital N. So we have the sum m and the product minus n. So by the relation between roots and coefficients, fa0 divided by a0 minus b0 and fb0 divided by b0 minus a0 are roots of the quadratic equation x squared minus capital Mx minus capital N equals 0. Moreover, since a0 and b0 are both integers, fa0 over a0 minus b0 and fb0 over b0 minus a0 are rational numbers. Or should I say, they are rational roots of this quadratic equation x squared minus mx minus n equals 0. And this quadratic equation have integer coefficients minus m and minus n. And this reminds us something, right? Therefore, by the conclusion of problem A, these two roots are also integers. And that concludes the final proof. And that's all for today's video. Thank you for watching, and please don't forget to hit the like and subscribe buttons if you enjoyed this video, and I will see you in another video.